Yeah, good morning, everyone. Glad to see you all here in this session. I'm Johannes, this is Katharina. We work for the Bavarian State Library in Munich, Germany. And we work in a team where we're developing search engines, workflow processes, and also maintain and develop our IIIF image API. And if you've ever been to Bavaria or read about it, you might have come across this little creature here. It's a Wolpi, which at its core is a pretty harmless animal that is made special by different appendages from different other animals that might serve a practical purpose, like the wings for flying or the antlers for defending itself, could also be purely decorative. And we are presenting our new IIIF image API server, which is a bit like a Wolpi, which is why we called it Wolpi. It's an extensible IIIF image API server. And at its core, it's pretty boring, actually. It's a ready-to-use image API server powered by libvips, so a pretty powerful image processing library written in C with support for a wide range of image formats. Also has the ability to plug in new formats, like or different parsers for image formats like Kakadu. There's an extension for that. And it has a very efficient and high-performance image processing pipeline, which is very important. It does lazy processing of images. What makes Wolpi special is that it can be extended through extensions written in regular JavaScript or Python, and thus adapted to different use cases, different domains. We'll see about that later. It's also easy to deploy. We have an official container image that you can just pop into Docker or Podman or your Kubernetes cluster if you have it. It tries to be cloud native, whatever that means. It has metrics, structured logging, health checks, so it should be pretty easy to run it in whatever environment you have. It's based on our experiences of developing and maintaining a custom IIIF image server for over 10 years, which got old, and we tried to kind of incorporate the lessons we learned while maintaining and developing it, and the kind of extensibility and the image processing parts were the most important improvements we wanted to make. And so this is why we wrote Wolpi. Let's talk about extensibility. What can you do? You can extend Wolpi to implement custom authorization schemes. So say, for example, you want to, you get the IP of the user, you get the set of headers, you get the cookies, and then you can write custom code to have custom logic to kind of check if the user should be able to access the image, or if they should be able to access it in a lower resolution. You could hook that up to a IIIF auth implementation. You could have your own SSO system that you hook up here, check for basically whatever authorization logic you have. You can make remote HTTP requests, look up stuff in a database, whatever you want. Same goes for resolving. So resolving identifiers to image sources, you are pretty free in that domain as well. You get the identifier, and then you can map it to a file system path, an HTTP URL. You could also fetch the image data from a database or an object storage. You could even go as far as kind of generating the pixels yourself based on some logic, like a shader, for example, if you want to. So yeah, it's pretty powerful. Even more powerful is that you can also hook into the image processing pipeline. So say, for example, you have an AI job in your cluster that needs a specific cropping strategy, like a center crop, which is pretty common in kind of image processing AI. And you can write an extension that implements a custom cropping verb for IIIF that then will apply your custom logic to your image and then proceed with the rest of the pipeline. So this is probably a niche use case, but it's very powerful since you have the full primitives of the libvips API available. So it has a very powerful set of low-level image manipulation tools that you can use to build really complex stuff. Pretty powerful. To let the world know about your augmentations to the image API, you can also manipulate the info.json. So to let the world know about your custom qualities, your custom features, and let clients handle it if they know about it. Yeah, some of you might have become a bit worried about this, kind of extending the IIIF image API verbs. Sounds kind of dangerous. Are we going to pollute the internet with broken implementations? Fear not. We tried to mitigate that a bit by mandating that whenever you enable a new extension in Wolpi, it must pass the full IIIF image API validation test suite. So This is not 100% safe, right? Bad faith extensions could kind of have their Volkswagen-like workarounds, check if they're being validated and bypass it. But I think it's a good defense against accidental breakage of the image API. So whenever you update the bumper version or change the configuration, it will revalidate the extension and see if everything still works. Extensions are made to be easy to distribute. So you can download them as a zip from somewhere and just put it in a folder and refer to that folder. But you can also just refer to an npm or PyPy package in your config. So just say, I want this package from npm in this version with this config, and Wolpi will automatically install it and validate it and enable it. As an example, we published a first extension to npm, which is a pattern-based, regular expression pattern-based resolver, where you just pop it in your config. Here is an example of an npm extension. It's Wolpi pattern resolver, version 0.1. And you pass it a config of resolving patterns, which is basically just regular expressions with capture groups that you can then map onto file system paths or HTTP URLs, which Wolpi will then use as the source for the images. And I think this is an extension that maybe solves a lot of use cases for resolving. If you have an identifier that can be directly mapped without any external lookups to a service, this is probably a good choice that you could take a look at. Yeah.
So if that doesn't fit your use case and you would like to implement your own extensions, you have the choice between two language runtimes, as we've heard, namely GraalPy, which is compliant with Python 3.12, or GraalJS, a JavaScript runtime that is compliant with the ECMAScript 2025 specification. In order to customize Wolpi's behavior, your extension will need to implement so-called hooks that are called by Wolpi at different points during request processing. And if you would like to log custom messages, expose custom metrics, or make your extension configurable in any way, you can do so by using the context API provided by Wolpi. So what does that look like in practice? We would like to show you a very simple sample extension. This is implemented in JavaScript. It's a single file with one object export, and the hooks are implemented as members of the object. So we have the info, cleanup, and resolve hooks. The info and cleanup hooks are mandatory, and they're used to provide metadata about the extension or to clean up any state that might have accumulated while processing a request. The actual logic in this case resides in the resolve hook. This is called every time you want to map an identifier to an image source, and Wolpi calls that while processing a IIIF image request. In this case, the extension first consults the extension-specific configuration object to find out which base directory was configured, and it then goes on to resolve part of the identifier against the base directory and return the file system path back to Wolpi, which will then load the image. Different return types would also be possible, not just file system paths, but also HTTP URLs, or even the raw encoded image data. And this is made possible by the GraalVM Polyglot API, which allows Wolpi, which is implemented in Java, to call extensions implemented in JavaScript or Python, and to pass Java host objects, such as the identifier string, to the extensions. This simple example could just as easily be implemented in Python, but there are certain differences between the two languages you might want to be aware of if you decide on which language to use for your extension. So the main difference is that JavaScript has a more limited standard library compared to Python's extensive standard library. With GraalJS, you don't have access to the node or browser APIs, but you're really just limited to what's implemented in or what's defined in the ECMAScript specification. This also means that the ecosystem is more restricted because you can't just install any package from npm, because they might rely on the browser or node APIs that GraalJS does not provide. This can in part be mitigated by using the Java host API at the cost of making your extension a bit more complex. But in our case, we, for example, have implemented extensions in JavaScript and have not encountered any problems so far. GraalPy, on the other hand, is compatible with many third-party libraries. It even provides experimental support for some native packages, such as NumPy. Although, if you would like to use a native package, we encourage you to check on their webpage to see whether it's currently supported. So once this decision is out of the way and you've decided which language you would like to use, you can get creative, because the extension API is actually quite powerful, as we've heard, and allows you to do much more than just implement a resolving strategy. So we would like to show you some more creative and not entirely serious examples of what you could do. So starting from this base image, this extension, as you see in the IIIF URL, adds a custom quality. It's an AI prefix followed by a user-generated prompt that describes how the image should be edited, in this case, colorize and add googly eyes. Or this one, in this case, the extension overrides the resolving hook to support dynamic image generation based on a user prompt. But you could also, for example, think of fractal images that allow users to zoom in and reveal ever more details. So, of course, you can plug AI models into Wolpi through extensions and use it, for example, for image generation, smart cropping, or image editing. And if you would like some more inspiration, we encourage you to check out the source code behind the two examples we have just shown.
Yeah, so a call to all developers, if you kind of got interested, have fun with the API. We're looking forward to seeing many creative and useful extensions. We're happy to help on GitHub. We're going to open up the discussions and issues. We'll also be available on IIIF Slack and at the conference, so just come hit us up with your ideas, questions, whatever. We're especially interested in your experiences with the extension API. So this is a first draft. We are looking for feedback from developers. If you hit any frustrations during development, roadblocks, stuff you feel could be more ergonomic, come talk to us. We'd be happy to bump the version to 2 and incorporate all your suggestions. So yeah, we're standing on the shoulders of giants. So here on the left we have some links to our source code and the source code for the pattern resolver extension. We have an extensive documentation that should basically cover all your questions, most of your questions, hopefully. Check that out. And many thanks to libvips, which is a really amazing piece of tech and very, very open to contributions. We made a pull request as part of the development and it was merged within, I think, 3 days. Like, pretty amazing. Also, this might sound weird, but many thanks to Oracle for publishing Graal. The Polyglot API is really amazing. If you're interested in polyglot programming, I recommend you check it out. It's really a brilliant piece of tech and very performant, surprisingly. Yeah, so thank you.
Hello, fellow humans. Welcome to this short talk on a visual tool we created to serve our metadata archivist. I'll discuss the design intentions, the standalone React app, and close with lessons learned. Today, I'll be presenting for both myself and my co-presenter. Hi, I'm Kait Sewell. I'm a senior software engineer 2 at Inotate. My co-presenter, who was unfortunately not able to make the trip to the Netherlands, is the brilliant Martin Lavelle, who is a senior software engineer 4 at Yale Library. And while not pictured but integral to the work, is JP Ingstrom, senior software engineer at Inotate, who also helped build this visual structure editor tool for IIIF ranges. While it may be obvious to everyone in this room, I want to start by centering on the why. Why were we creating this tool? We weren't hopping on the bandwagon because ranges were the hot new thing. We saw the opportunity structures provided, because the way a user navigates through a piece can vary wildly, and if we can guide that journey and share multiple ways to explore the work, then the user is given the widest array of paths through discovering an archival item. And providing these multiple pathways provides us the chance to tell multiple stories, So of course, we wanted a way to provide as many stories as possible. And 4 years ago, we set about building a tool to create these structures. As with many solutions, we started with a problem. The issue was we had nothing that could manipulate this new information other than manually editing IIIF manifest JSON files, which, as one can imagine, was slow, error-prone, and it was hard to visually parse the images as text. So rather than continuing with the manual JSON editing process, we explored what existed in the landscape. Up until yesterday, the only other existing tool I knew of was built by Diggerati. Diggerati created this really neat tool that provides an editing interface for manifests that we got to see a demo of yesterday. Both projects were started in the same time frame, and I was unfortunately unfamiliar with their work until I started working on this presentation, and one of my coworkers at Yale shared their solution with Martin and I. So I'm hoping to explore their code base in depth soon. There are other solutions out there as well, like Smithsonian's Voyager and IIIF, but I'm sure there are more. So while both of these projects were started around the same time, I and the rest of my team were unaware of these existing solutions. So that meant we got to take advantage of some greenfield development. Honestly, as an engineer, there are few things that are more enjoyable to work on than greenfield development and the wide array of possibilities a fresh slate presents. We started with knowing we wanted the process to be easy for our metadata archivists and fun if we could manage it. We aimed for the solution to be highly visually appealing, intuitive in operation, and designed for archivists first. Because we wanted a highly visual and interactive experience, we developed a standalone React app that would interface with our existing management system that is based in Rails. So this gave us a strong visual presence and a seamless flow for the admin user. And now I'll finally show you what it looks like. This is what the visual structure editor tool looks like with a manifest loaded and some of a table of contents generated. The controls are very similar to the file folder operations on a Windows system because that's what our metadata archivists were already familiar with and already working with. We intentionally kept it as text-free as possible so we could lean heavily into the visual language by eliminating text and using symbols instead. The same multiple select operations one is used to in a file folder is the same logic we use in the structure editor tool. On a trip to campus a few months ago, I had the privilege of speaking with some of the metadata archivists who use the tool on a regular basis, and they were so pleased with it. While it took some getting used to, the tool was intuitive and easy to use. And they were very grateful we had sorted out the recent bug we had in the system, but I'll get to that at the end. It was really enlivening to know that something I helped build was actually working exactly as designed. The range builder was also designed to operate the text editing controls much like a Windows file folder system, except we added a drag and drop reordering of ranges. Labels for ranges are free edit text fields. There's the potential to create infinite nested hierarchies because we wanted our admin users to have as many options as they could imagine. We wanted the tool to feel familiar, so we achieved this through mirroring the operations of the operating system the metadata archivists were already working with. So once an archivist has arranged and rearranged to their heart's content, what are they left with? The output of the tool is valid IIIF syntax for structures, ranges, and canvases that follows expected conventions and behaves as designed. At this point, the structure is saved to the database and a new IIIF manifest is generated, which is then representable in any IIIF viewer. In Yale's implementation, they use Universal Viewer as their IIIF viewer, but this would behave similarly in any IIIF viewer. As one can see, there is another tab for the index next to the thumbnails that gives the front-end user the capability to take advantage of the custom-created table of contents created by the metadata archivists. A user is able to navigate through the work with the guide of the descriptive ranges provided by the metadata archivists. The visual structure editor tool produced a structure section in the manifest that is being read by the IIIF viewer and rendered to the user reliably and consistently. The structure section in the IIIF manifest is a nested hierarchy of ranges that contain either more ranges or canvas items. The underlying logic within our tools and systems creates a compliant IIIF structure section that is consistently readable by any IIIF viewer tool. I wrote a blog article that goes into more detail into the models and relationships and logic that manages how it controls the careful output of the structure editor tool, as well as how all the pieces fit together, in case anyone is interested in implementing any of this open source code into your own project. And I don't see him, but I'd like to give a little shout out to, hey, James from the British Library, read the blog article, was able to get it working on his computer locally, so I can know that it will work for you. So thank you, James. There's a link to that blog article at the end of the slides, which we are not far from, but now it's time to share one of the lessons we learned over the 4 years of this tool being in operation. So out of seemingly nowhere, metadata archivists started reporting that duplicate ranges were being created, which after years of no issues was pretty surprising. Almost as surprising as the squash bugs that destroyed my zucchini last year, this error was tenacious. It was one of those errors that was hard to reproduce reliably, happened only sometimes, and there was no obvious pattern as to why it was happening to some objects but not others. You know, the fun kind of bug that appears out of nowhere and has a source that is a deeper mystery. I fared better with this bug than the squash bugs last year, and that we fixed it from happening again. So while I have no idea what the squash bugs have intended for me in my garden this year, I do know I won't see the duplicate ranges ever again, because we were able to protect against it. The way we solved the bug was to add a unique index to the resource ID in the database schema, and I suggest you do this as early in the process as you can. Doing it early may save yourself from needing to clean your database of all the duplicates that already exist, or as in was our case, all 4 of our deployed environment databases. So because, as many of you know, you cannot add a unique index until no duplicates exist. So my suggestion is to save yourself the headache and just start with a structure table, structured, pun intended, like so, with the unique index in place from the get-go. Of course, this wasn't the only lesson we learned. Should you endeavor on a project like this one, I would like to suggest some things from the lessons we learned over the past 4 years. First is to add constraints early, whatever they are. Add them early to save yourself from the cleanup later. Second is that React was the right decision for us at the time. Perhaps there is a new flashy solution out there that we could upgrade to, and who knows, we may. But for its functionality, React was the right solution, and it made sense to really depart from the norm to build a bespoke solution for our users. And it was worth departing from the norm to provide the best experience. Last is that we held the metadata archivist's needs in mind while we designed and while we built the solution. And I can attest from recent data gathering from the admin users themselves, this was also the right call. I know, crazy, design for your users. So when I'm coding away in the darkness, it's rare to get that face-to-face time. So it really meant a lot to be able to meet those metadata archivists in person and hear firsthand how well they like the tool my team and I had put so much thought into. I've been working on Yale Library's digital collections site since 2020, 2021. Time is hazy back then. There was a pandemic. It's wavy. But I still pinch myself that I have the fortune to work in open source and open data. Things I care deeply about, I get to devote a large portion of my time to making better. It's usually by breaking things, but well-intentioned. We broke a few things over the course of this tool's creation, but we ended up with a solution that works well and has continued to work well over the last 4 years. All of these projects are available publicly on GitHub, so feel free to peruse at your leisure and dive in as deeply as you wish. Please feel welcome to reach out to me via email if you have any questions regarding the implementation or about how to get something to work for one of your projects. I've written a blog article that goes into detail behind the models and logic about how the tool was built and how it fits into our existing code base, in the hopes that it may help explain how all these things work together to create new visual stories for users to discover works in the collections. So that's that. The Visual Structure Editor tool for IIIF ranges is in the 4th year of operation, and we may have chatted about being able to import spreadsheets for ranges while we had that on-campus visit, so the future may hold some interesting updates. Everyone, thank you for your time. It's an honor to be able to present, and thank you again, and hope you have a great rest of your conference.
Hi everyone, I'm Paul from near Paris, École des ponts et chaussées, and I'm here to present to you aiiinotate, a fast and scalable annotation server for IIIF. So before I dive in and start talking about what an annotation server is and how ours work, let's talk a bit about what annotations are. So, what is an annotation? Let's start with a concrete use case. You have manuscripts and you want to identify images in them. So you don't have your physical manuscript with you, but you do have a digitized IIIF manifest available. So what you do is that you want to view what's in the JSON, so you open it in a IIIF viewer such as Mirador. And there you go, you can visualize your data. You look through the pages and then you stumble upon an illustration. What you then do is that you identify this illustration by drawing a bounding box around it, and you comment it with an identification of your illustration. And there you go, you've done an annotation. So in more concrete terms, an annotation connects a body and a target. The body is comments and tags that are metadata that is, commenting on the target, which in our case is a canvas and a bounding box. So this is an annotation. What you want to do now, once you've looked through all your manifest and you've stored and you've found all your images, is that you want to store those annotations. You want annotation persistency. So you want an annotation server. For this, there are several solutions, such as Simple Annotation Server, Inotate, MyFi, CatchPy, and others. And now we present to you a new solution, aiiinotate. So aiiinotate is a solution to a specific problem, which is that with computer vision and AI, we have a massification of data being created. For example, if you have a region extraction algorithm, you're going to be able to detect automatically images such as illustrations or diagrams, and those pretty much, detecting those image regions pretty much generates IIIF targets. If you have an image classification algorithm, you're going to be able to say, this image is a diagram, this image is a character, this image is a text line. And so you're going to be able to create IIIF annotation bodies. And so you're creating data that can be stored as IIIF annotations, but you're creating this at a very large scale. And well, we couldn't really manage working at this scale with existing annotation servers, and so we decided to create our own, and this is aiiinotate. aiiinotate's goals are fairly simple. First off, we want to be fast and scalable. This means that we want to be able to store millions of annotations, and we want to be able to access them quickly, very quickly, ideally. Second off, we want aiiinotate to be easily integrable in your own workflows. The rationale is that if you start to use aiiinotate, your life should be somewhat easier than before, hopefully. So first, let's talk about speed and scalability, and to talk about that, let's view a bit what's inside aiiinotate. At its core, aiiinotate is a database. This database stores IIIF annotations in JSON format. For the database, we use MongoDB, which was kind of an obvious choice because Mongo stores collections of JSON documents, so a MongoDB database. On the other hand, we have a client that is hopefully you, who has annotations and who wants to store them inside this database, and so who wants a communication route with this database. So in the middle, we have an interface, which is IIInotate's web app. IIInotate's web app provides a REST API, which allows users to communicate with the database through HTTP requests. So you send an HTTP request to the web app, it will write annotations in the database, or you want to fetch annotations, you make another HTTP request, and IInotate will send you back JSON. Fairly logical and normal stuff. The web app is built using Node.js, both because it's fast and because it's fully asynchronous, which means that we'll be able to handle concurrency and concurrent client better. For example, if you have 20 different apps that want to read from Inotate, theoretically it should be able to do that. Inside Inotate, there are two important modules that I should talk about. First off is Fastify. It's the web framework we use. So Fastify is a Node.js web framework that's built for speed, and that's also fully asynchronous, so it was kind of an obvious choice to use it. Another important thing that we use is AGV for data validation. So AGV is bundled with Fastify, and what it does is that, for example, if you want to write an annotation inside Inotate, what we're going to do is that we're going to receive this annotation, and before doing any processing, we're going to validate your incoming annotation against a JSON schema of what a IIIF annotation should look like. If your IIIF annotation is valid, we go ahead and process it. If not, your request stops right there, and we avoid doing any extra processing. So the goal is to save the processing for data that is actually valid. Looking at Inotate's designs, at the end of the day, we don't have that many minute optimizations. When I started doing this, I really thought that I would have to go very deep into like small optimizations. But in the end, we just do some caching and memorization. We rely a lot on early on data validation to be able to be, to validate data quickly. And that's pretty much it on the web app side. We also do have a 90% testing coverage, so if you want to make the app crash, well, it's going to be slightly more difficult than normal. On the database side, to make things faster, what we do is that we store full IIIF annotations. There's a trade-off going on here, because what this means is that your database will be heavier than it could be, because we're going to store entire annotations, and so we're going to store redundant fields from one annotation to the other. The big optimization trade-off, the big advantage that this provides is that if a client wants to read an annotation, what we just need to do is find it in the database and send it to you as is, and we don't have to lose time doing complex reformatting of the data so that it can become valid IIIF. We also do have, obviously, database indexes to make your annotations, to make your queries run faster on frequently queried fields. So this is pretty much a summary of how Inotate works. I talked about annotations, and this is what an annotation looks like in the database. So pretty standard IIIF annotation. In pink, you have your annotation body. In green, you have your annotation target. And if you look more closely, we do add some non-standard fields, which I think are generally useful. First off, we use canvas index to store the position of an annotation inside the document. So what happens is that when you insert an annotation, we're also going to fetch the related manifest and to find the position of the target canvas inside that manifest. The idea then is to be able to answer questions which, if you work with books, are fairly normal questions, such as which page is this annotation on, or I want to find all annotations between pages 700 and 730. So we store that information. Then the second non-standard field that we add is an XYWH bounding box of the annotation's targets. So what we do is that when we insert an annotation, we find and define in pixel space the position of your annotation on the canvas or page. The rationale here is that if a client needs this bounding box to be accessible, it wants the bounding box to be accessible fast, and depending on how your annotation is defined, it can be non-trivial to retrieve that information. For example, if you want to calculate the bounding box of an SVG target, it's not going to be extremely easy, and it's going to take time. So what we do is that at insert time, we calculate this bounding box, and then a client can access it directly. So this was the Inotate annotations inside the database. Now let's talk a bit about how we communicate with aiiinotate. This is a summary of most of aiinotate's API. So these are all or most of the HTTP routes that are used to communicate with aiinotate. So as you can see, it's fairly simple. It's just routes to do all create, read, update, and delete operations in the database through HTTP queries. We did put a lot of emphasis on batch operations. For example, you can create thousands of annotations at once using a create many route. You can delete all annotations inside a manifest using a delete many route. Similarly, you can read the data and find all annotations in a single canvas, in a single manifest, or count all annotations within a manifest. To read all annotations in a manifest, we have implemented a IIIF search API and have extended the IIIF search API actually with a canvas min and canvas max URL parameters that allow us to profit of the canvas index thingy that I presented earlier. So with this, you're able to fetch, for example, all annotations within a certain page range or within a certain canvas range, or all annotations on a specific page. Obviously, we also do provide routes for operations on single annotations, so you can read one annotation, create it, update it, delete it. Most of the API is heavily inspired by Simple Annotation Server, so I want to thank them. So this is a summary of most of our API. Now, I said that I wanted to be scalable and fast. So what we did is that we did a benchmark to test how well aiinotate works So how this benchmark works is that we may create a database of increasing size. So first off, we start with having 100 annotations in our database, then 1,000, then 10,000, up to 10 million annotations. And then at each database size, we're going to execute a bunch of HTTP queries on aiinotate to test how well and how fast it responds. So we try to read a single annotation, read an annotation page or an annotation list containing 100 annotations, write 100 annotations in a single query, delete an annotation. We execute each of these HTTP queries 50 times, and then time the average execution times. And the results are here. What we can see is that, first off, and replies from aiinotate are fast. All routes reply within 1/10 of a second and 100th of a second, so it's fast. Second thing that is what's the most reassuring thing for us is that results are constant from one database size to another. This means that there's no huge drop-off in performance going above 1 million annotations, which really leads us to believe that aiinotate can be scaled and does scale in practice. So this concludes the fast and scalable part, and now let's talk about easy integration. First off, aiinotate is fully compatible with Mirador 4. This means that you can read aiinotate data from Mirador 4. You can write aiinotate data from Mirador 4 as well. We did this by using Mirador Annotation Editor, which is a fantastic plugin developed by the good people of Tetras Libre, and for which we contributed an aiinotate adapter, which basically connects Mirador Annotation Editor with aiinotate. And what you can see on the code block on the left is that basically in a one-line config, you can connect your aiinotate with Mirador, and everything will run smoothly from there on. Secondly, we have worked quite a bit to make aiinotate as easily usable as possible by end users. It's distributed as an NPM package, so you install the package and then you just create your database and you're good to go. You can also use it as Docker. We have a reference Docker implementation that's going to grant you a Docker Compose with, on the one hand, a Dockerized Mongo database, and on the other hand, an aiinotate instance. And finally, we have also worked on doing a reference implementation of Mirador with aiinotate, which can be used either through NPM or as a Docker Compose, which will give you a Mirador web app, an aiinotate instance, and a Dockerized Mongo database. So as you can see here, in less than 10 lines of code each time, you have 3 different ways to use aiinotate fairly easily. It's all configurable with a very easy .env file, so that you can tailor it to your needs. Finally, or not finally actually, we've done a command line interface that is used for all operations on aiinotate. So you can manage your database through aiinotate. Through this aiinotate CLI, you can import data, export data, and run aiinotate throughout this command line interface. To use aiinotate in your projects, currently the presentation API version 2 is fully supported because this is the one that we use in our workflows. And support for the presentation API v3 is planned in the future, and v4 in the furthest future, since I heard it's been released. It's also a fully open source software license under GPL v3. To finish, aiinotate is not just like a proof of concept. We do actually have a use case for it, which is IIICON. IIICON is a platform that bundles together historical corpus curation and computer vision tools. It uses IIIF throughout its entire image collection management and uses IIIF annotations to store results of computer vision experiments. For example, if you do region extraction, you're going to generate IIIF annotations. And we use aiinotate to store those IIIF annotations. And in practice, currently, we have 3 instances of IIICON that are in production with aiinotate bundled in them. And the largest one is currently stores up to more than 500,000 annotations, actually, in production. So there you go. I hope I've convinced you that aiinotate is usable and practical, and I'm ready. I'm available for questions.